Hi there, we're going to start section 4.2, which is called Trigonometric Functions of Acute Angles. And we're going to focus on what's considered to be right triangle trigonometry as we go through this section. So before we start, I want you to kind of ponder a question that I have up here on the screen. What is the least amount of information needed to classify two right triangles as similar? If you think back to your geometry days, what would the answer to this question be? The least amount of information. So least amount of information needed to classify two right triangles as similar. So if you think about that a little bit, the least amount of information that we would need would be information about an acute angle of one triangle equal to an acute angle of the other triangle. I guess I should say of one triangle equal to an acute angle of the other triangle. So if we know that an acute angle of one triangle is equal to an acute angle of the other triangle, we can automatically assume that the two triangles are going to be similar. This may come into play a little bit later on as we go through some of the information in this section, but good thing to review from geometry at the least. So if we know theta is an acute angle, then we also know in this next line, so theta is an acute angle. Remember, an acute angle is an angle between 0 and 90 degrees. Then there are 6 distinct trig ratios of side length that can be determined. So we have 6 what we consider to be trigonometric ratios. And we're going to go through these 6 ratios on the next screen. Each ratio is a function of theta. So that means we can write these as a function of theta, and knowing that theta falls between 0 and 90 degrees if we're working in degree measure, or theta falling between 0 and pi over 2 radians. Since pi is representative of 180 degrees, 180 degrees divided by 2 is our 90 degrees, so pi is equal to, or pi over 2 is equal to 90 degrees. So not too much information on this screen except for the fact that given an acute angle of a right triangle, we're working out of a right triangle here, we can come up with 6 distinct ratios that are going to correspond to side length. And as I turn to the next screen, before we get into those 6 ratios, we're going to talk about what it means to put something, an angle measure in standard position on the coordinate plane. So I had briefly in the video in 4.1 mentioned the fact that we can have angle measures that go beyond 360 degrees or angle measures that are actually negative. So I want to illustrate that a little bit here with what's called the standard position of an angle on a coordinate plane. Now we want to make sure that all of our angles kind of have the same setup when we draw an angle. That's not a very straight line, is it? Let's see if I can erase it and make it better. So if we draw a coordinate plane, we're going to label it X and Y for our axis lines. We're going to start to draw our angles on a coordinate plane so that we all kind of have the same setup. When we look at something, we all know that we're looking at the same thing. The vertex of our angle is going to be at the origin. And every angle we know has 2 rays. So one of our rays is going to come out along the positive x-axis. That's going to be called the initial side. The initial side, or the initial ray. That angle, or that ray, is going to stay stationary. There's no rotation to that ray at all. The other ray, which is called the terminal side, is going to be the ray that moves. So pretend that they're both starting on top of each other right here on the initial side. And then one of the rays is going to pick up and start to rotate around the coordinate plane. Wherever that ray stops, this ray is called the terminal ray, or the terminal side of the angle, is how big we can indicate our angle measurement to be. So when I open this up, I went in this direction, which means that I went in a counterclockwise direction, and I can name this angle here theta equals, I don't know, we went over 90 degrees, so maybe 135 degrees. It looks like it's almost bisecting that second quadrant. Anytime we have counterclockwise rotation, that's a positive angle measure. So that angle that I just drew is positive 135 degrees. You could convert that over to radian measure if you wanted to do that. That would be 3 pi over 4, I believe. You might want to double check my work on that. But every angle has a negative partner, or we can also draw angles in the negative respect. Negative meaning the direction of opening only, as far as measurement goes. So if I were to stay on this and start with my initial side here again, but this time I rotated my terminal side, so I went this way in a clockwise direction. The terminal side is exactly the same as what I had in the positive 135 degree angle, but this time I would name this angle as, let's call this one alpha. It would have a negative angle measurement because of the direction of opening, since it's moving clockwise, and it would be negative 225 degrees about. If theta was positive 135, alpha would be negative 225 degrees. Together, they make up one full revolution. So if you were to subtract the two of them, we would get, if we did 135 minus 225, we would get that one full rotation. So counterclockwise is a positive angle measure. Clockwise is a negative angle measure. So depending on what type of movement we have to make around the coordinate plane will depend on the positive or negative sign in front of our angle measure. Now we can also, while I have this drawing here, I might as well talk a little bit about those angles that I mentioned in section 4.1 that are larger than 360 degrees. If I draw my coordinate plane, and I want to draw an angle, for example, what if I say that theta needs to be 1,240 degrees? Well, I know that that's positive, so I know I'm going to go counterclockwise. And if I start off my initial side here, I know that one revolution around is going to bring me to 360 degrees. 2 revolutions will bring me to 720 degrees. Another revolution, full revolution around, will bring me to 1,080 degrees. So if I'm at, with 3 full revolutions, I'm at 1,080 degrees. I need to go another 160 degrees in order to complete the 1,240 degree angle. So here's 90, and then I need about another 70. So maybe we'll make our terminal side right here. And I'm going to put an arrow here right before it gets to the terminal side so I know which way this rotated. The fact that I started above the x-axis and moved in this direction also tells us that is positive, but this angle theta is 1,240 degrees. So the spirals there tell us how many times we actually went around in full revolutions. Here's 1 full revolution, 2 full revolutions, 3 full revolutions, and then we did from here to here is another 160 degrees. So a 1,240 degree angle looks exactly like a 160 degree angle, except for we have additional spirals going around the coordinate plane. Same kind of thing would happen if we were going in a negative direction, except you would move in a clockwise rotation around the coordinate plane. So, get this information in your notes, and we'll talk a little bit more about graphing these in a standard position and positive and negative angles, as well as angles that fall over 360 degrees or 2 pi radians. So now we're going to jump back to what was on the first screen here, these 6 trigonometric ratios. And you, I will guarantee, heard something in geometry class that related to 3 out of these 6 trigonometric functions. That was the mnemonic SOHCAHTOA. SOHCAHTOA. Whoops, I spelled it wrong. SOHCAHTOA. And The S stood for sine. The C stood for cosine. And the T for tangent. And the OH is opposite. H, hypotenuse. I'm going to run out of room here. A is adjacent. H again is hypotenuse. I'll just abbreviate it HYP. O is opposite again, and adjacent is ADJ again. So sine is the opposite side over the hypotenuse, cosine adjacent side over hypotenuse, tangent opposite side over adjacent side. What that means is that if I were to draw a right triangle, and here's my right angle, and I called one of these angles theta. We'll call the bottom angle here theta. So the side across from theta is considered to be the opposite side. The side directly that makes up one of the rays of theta is the adjacent side. And then we have our hypotenuse, remember, across from our 90-degree angle. So the sine of theta is equal to the opposite side length over the hypotenuse. It's probably important that you set your paper up to look like this with the two columns of these 6 trig functions. It's going to help you learn the relationship between them. Cosine is the adjacent side length over the hypotenuse length. And tangent is the opposite side length over the adjacent side length. That's all coming from SOHCAHTOA. Now those you should be fairly familiar with from geometry class, and you should be kind of remembering the SOHCAHTOA idea as we go through here. What you may not be as familiar with are the other 3 trigonometric functions: the cosecant of theta, the secant of theta, and the cotangent of theta. There's a relationship between each of these functions and one of the 3 functions from SOHCAHTOA. The functions in the second column and the first column are reciprocal functions. So these are considered to be, let's see, these are considered to be, if I can block this off, reciprocal functions, which means that going across in columns, these functions are reciprocals of each other. So the cosecant function is hypotenuse over opposite. The secant function is hypotenuse over adjacent. And the cotangent function is adjacent over the opposite. So if you know SOHCAHTOA, you basically know all 6 trigonometric ratios. The 3 coming from SOHCAHTOA, sine, cosine, and tangent. And then knowing that sine and cosecant are reciprocals of each other, cosine and secant are reciprocals of each other, and tangent and cotangent are reciprocals of each other, you're very easily able to find the trigonometric ratios for each of those other new 3 trig functions that we're working with. So you definitely need to learn these definitions coming off of SOHCAHTOA, and you need to understand the relationship between the the first column here and the second column being reciprocal functions, and vice versa. Remember, the first column is the reciprocal of the second column is the reciprocal of the first column. So you do need to learn those ratios and come in with any questions you might have from anything you might have learned before in geometry class that you didn't quite understand. So we're going to use these 6 ratios an awful lot as we go through the rest of the course. It's going to be crucial that we understand them with relation to our 2 special right triangles that we studied in geometry, that being those being the 45-45 right triangle and the 30-60 right triangle. So if we start off with a 45-45 right triangle. And we're going to draw these, make sure you draw these in your notes with me here, just so that we can set up the ratios here. If you remember from geometry class, the two legs of a 45-45 right triangle can be identified as x, and that makes the hypotenuse x radical 2. So if I'm concerned about finding the 6 trig ratios, for 45 degrees, okay, of a 45-degree angle, because that's the only angle we have, only acute angle that we have in that triangle, then we can say, I'm going to do this just to make things a little bit easier. I'm going to force, if the hypotenuse is 1, and there's a reason why I'm forcing this hypotenuse equal to 1, because it has something to do with what's called the unit circle we're going to study a little bit later. If our hypotenuse is equal to 1, then hopefully you agree with me that x radical 2, hold on, then x radical 2 equals 1. So if our hypotenuse is equal to 1, then the generic length, which is represented by x radical 2, is equal to 1. And x then would be 1 over radical 2, or radical 2 over 2. So if I were to make the hypotenuse equal 1, then each leg would measure radical 2 over 2, radical 2 over 2 units long. So if I'm trying to look at the 6 trigonometric ratios, the sine, SIN is the abbreviation for sine, and I always put the angle measure that I'm referencing next to it. If I don't know it, if it's unknown, I write theta or alpha or beta, but if I know the angle measure either in degrees or radians, we write the angle measure after the trig notation. The sine of 45 degrees is opposite over hypotenuse, which I'm going to use this angle as my 45-degree angle. I could use the other. They're both going to turn out to be the same. It's going to be radical 2 over 2 over 1, which is just radical 2 over 2. The cosine of 45 degrees is adjacent over hypotenuse. Now the adjacent side is this side right here for that angle. So radical 2 over 2 over 1 again, which leaves us with radical 2 over 2. And then the tangent of 45 degrees, which is opposite over adjacent. So opposite over adjacent is radical 2 over 2 over radical 2 over 2, which is just 1. So our 3 base trig functions for a 45-degree angle turn out to be sine is radical 2 over 2, cosine radical 2 over 2, and tangent is equal to 1. That means that I can very easily now find the 3 reciprocal functions. The abbreviation for cosecant is CSC of 45 degrees. That's going to be the reciprocal of radical 2 over 2. So that's 2 over radical 2. And if we want to rationalize that, that will leave us with, rationalize it by radical 2 over radical 2. We get 2 radical 2 over 2, which is just radical 2. Secant, SEC is the abbreviation of 45 degrees, is going to be 2 over radical 2. That's the reciprocal of cosine, which after we rationalize also gives us radical 2. And then the cotangent abbreviation COT is the reciprocal of the value of 1, which is just 1. So the 3 reciprocal trig functions have values of radical 2, and 1. It's really, really, really important that you learn these 6 values. Sine, cosine, tangent, cosecant, secant, cotangent of a 45-degree angle. Make sure you get this in your notes. Write down any questions you might have with the 45-degree angle, because I'm going to move on to the 30-60 triangle here as I erase the screen now. We might as well get this information completely out of here. And we're going to focus on the 30, 60, 90. So I'm going to label this triangle with the 60-degree angle at the base and the 30-degree angle up above. And we'll focus on the generic sides first of all. If you remember from geometry class, the side opposite the 30-degree angle is x, opposite the 60 is x radical 3, and opposite the 90 is 2x. So there are generic representations. And I'm going to do the same thing. If the hypotenuse equals 1, then we can say that 2x is equal to 1 and x is equal to 1/2, which means that if this represents 1, then the side opposite the 30-degree angle is 1/2 in length, and the side opposite the 60-degree angle is radical 3 over 2. It's 1/2 times radical 3 as far as its length goes. So I'm going to look at the 6 trig functions first of all for a 60-degree angle. So sine of 60 degrees, cosine of 60 degrees, tangent of 60 degrees, and then cosecant of 60 degrees, secant of 60 degrees, and cotangent of 60 degrees. All right, so sine we know is opposite over hypotenuse. So if this is my 60-degree angle, the side opposite is radical 3 over 2 over the hypotenuse, which is 1. So that leaves us with radical 3 over 2. The cosine of 60 degrees is adjacent, which is 1/2 over the hypotenuse, which is 1. So we just get 1/2. And the tangent of 60 degrees is adjacent or opposite over adjacent. So opposite is radical 3 over 2. Adjacent is 1/2. And if we simplify this complex fraction, we have radical 3 over 2 being multiplied by 2 over 1, which is just radical 3 because the 2's divide out. So our three base trig ratios, the sine of 60 degrees is equal to radical 3 over 2. Cosine of 60 degrees is 1/2, and the tangent is radical 3. Knowing that the other 3 functions are reciprocals, then we can say that the cosecant of 60 degrees is 2 over radical 3, or if we rationalize, we end up getting 2 radical 3 over 3. The secant of 60 degrees is equal to 2. And the tangent of 60 degrees is equal to 1 over radical 3. And if we rationalize, we get radical 3 over 3. So the 3 remaining trigonometric functions in rationalized simplified form are 2 radical 3 over 3, 2, and radical 3 over 3. Again, should definitely know these values for a 60-degree angle. Write down any questions you might have with that, and we'll go through and we will do the 30-degree angle down here. So if we're working with 30 degrees, we want sine of 30 degrees, cosine of 30 degrees, tangent of 30 degrees, cosecant of 30 degrees, secant of 30 degrees, cotangent of 30 degrees. All right, this time we're going to be focusing on the angle up here. So sine is opposite over hypotenuse. That's going to be 1/2 over 1, which is 1/2. Cosine of 30 degrees is adjacent, radical 3 over 2 over 1, which is radical 3 over 2. Tangent is opposite, 1/2, over adjacent, radical 3 over 2, which will simplify into 1/2 times 2 over radical 3, which gives us 1 over radical 3. And if we rationalize that, we get radical 3 over 3. There's a lot of simplification involved in that step. So 3 base trigonometric ratios. Sine of 30 is 1/2, cosine of 30 is radical 3 over 2, and tangent of 30 degrees is radical 3 over 3. So knowing that we have 3 other reciprocal functions, cosecant of 30 will be 2. Secant of 30 will be 2 over radical 3, which rationalizes to radical 3 over 3. And cotangent, I'm going to actually go right here to flip and take the reciprocal of. So this is just radical 3. So our other three ratios are cosecant of 30 degrees is 2, secant of 30 degrees is 2 radical 3 over 3, and cotangent is radical 3. Again, need to know these values. What I want you to try to do right here from this screen is to make a connection between the trigonometric ratios of 60 degrees and the trigonometric ratios of 30 degrees. There's a connection between the two of them. I could also have said 60 degrees, this is the same as pi over 3 radians, so this could all be in radian measure, and this is pi over 6 radians. So don't be surprised if you hear me talk about radian measure as opposed to degree measure. Let me know in class if you have any questions on this when you do come in to the next class period. But super important. I can't stress the importance enough of the information on this page. Now the next piece is going to be an example where I'm going to give you information about one of the 6 trig ratios, and we need to find the other ratios. So let theta be an acute angle such that the sine of theta is equal to 5, 6. We want to find the other 5 trigonometric ratios. So my suggestion would be that you draw yourself a picture. We know that these are right triangles. I'm going to make theta down here. Now, I don't know the angle measure of theta, but what I do know is that the sine of theta is equal to 5, 6, which means that I know that the side opposite the angle theta is equal to 5 units, and the side which represents the hypotenuse is 6 units long, which means that I technically can find that missing leg. That missing leg will be, remember Pythagorean theorem, 6 squared minus 5 squared. So x squared will be 36 minus 25, or 9. Is that right? No, 11. What am I saying? So x will be equal to the square root of 11. So this leg measures radical 11 units. Leave it in radical form. Don't change it over to decimal form. Remember, radicals are the most accurate way to represent your answer. So now that we know all 3 sides of the triangle, we can complete the other 5 trigonometric ratios. Cosine will be adjacent, radical 11, over hypotenuse 6. Tangent is going to be opposite over adjacent, 5 over radical 11, which rationalized will give us 5 radical 11 over 11. If I know sine, I automatically knew cosecant as well, so that's 6/5. Secant, which is the reciprocal of cosine, will be 6 over radical 11, or 6 radical 11 over 11. I do want you to rationalize these. And cotangent of theta, I'm going to go to this step to get the reciprocal, radical 11 over 5. So if you know one of the 6 trig ratios, it's going to be enough to help you complete your right triangle. And once your right triangle is completed, you can find the remaining 5 trig ratios using the idea of SOHCAHTOA and the reciprocal functions. So not too tough. You just have to kind of work your way backwards in order to complete your triangle. That's the most important thing, is make sure that your triangle is complete before you move on. So what we've done so far has been doing things longhand, going through and using the idea of SOHCAHTOA in order to compute the 6 trigonometric ratios. We're not always going to have a situation where our angle measure is nice, where it's one of our 30-60 or 45-45 right triangles, or we can complete the triangle in order to find the 6 trigonometric ratios. So we can use our calculators here. I'm going to ask you to pull your calculator up just so that I can go through some of the processes with you. There is a degree mode and there's a radian mode on your calculator. I'm not sure if you knew that or not, but if you hit the mode key, you notice in the third row here, you have radians and degrees. So one common error when students use their calculator to get trigonometric ratios in decimal form is that they have their calculator set to the wrong mode. So you have to make sure that your calculator is in the right mode for what you are trying to find. The other thing is that the cosecant, secant, and tangent functions, or cotangent functions, the reciprocal functions, are not on your calculator as straight keys. Sine, cosine, and tangent are. You see me pushing those buttons. But if we want to work with the reciprocal of sine, which is cosecant, so cosecant theta is the same as 1 over sine of theta. That's exactly what we have to punch into our calculator. We've got to do 1 divided by 1 divided by, oh, now I've got to, 1 divided by the sine of whatever our angle measure is. That's the equivalent of cosecant. Secant is going to be 1 divided by cosine. And then cotangent is going to be 1 divided by tangent. So you've got to make sure that you're using the right approach to a problem in order to do those as well. I'm going to pull the notes back up, and I have 2 examples down below that say evaluate the following on your calculator. The first is the cosine of 27 degrees. So have your calculator handy, and let's just make sure that we know how to input this into our calculator. Cosine of 27 degrees, I kind of lost my train of thought there as far as what we were looking at. I'm going to double check my mode, make sure I'm in degree mode, and I am. And then I know that cosine is on here, and I'm going to just type in 27. And what the calculator is going to give me is a decimal approximation of the ratio. So the cosine of 27 degrees is approximately 0.891. That doesn't have a label on it because it's a ratio. So cosine of 27 degrees is approximately 0.891. The next one I have is the cosecant of 2.5. Cosecant of 2.5. Now, because there's no degree symbol there, this is implied to be in radian measure. So when I go to my calculator this time, I'm going to erase what I had here. I'm going to clear it out of here, and I'm going to make sure that my mode is in radians. So if I want to do the cosecant of 2.5 radians, then that means that cosecant is not a key on here, but I know it's a reciprocal of sine. So I'll type in 1 divided by the sine of 2.5. And I get an equivalent approximation of 1.671. So you should become good at using your calculator for evaluating trig ratios that are not commonplace, not the 45-45 or 30-60 right triangles, and it will be okay for you to use your calculator during those times. All right, we have one more little section to do here, and it has to do with some applications. So word problems. In order to solve a triangle, we solve a triangle when we use some parts of the triangle to solve for all 3 angles and all 3 sides. A triangle is completely solved if you know all 3 angles and all 3 sides. So some of our problems will be, please solve the triangle. Other problems may be, given a scenario, you just have to find the height of a tree or something like that. So this example here says a right triangle with a hypotenuse of 8 includes a 37-degree angle. Doesn't say which of the 2 angles it is, but we know that one is 37 degrees. Find the measures of the other 2 angles and the lengths of the other 2 sides. So we're basically solving this triangle. You should always draw yourself a picture so that you know what's being presented to you. So we have a right triangle. We know that one angle measures 37 degrees and it has a hypotenuse of 8 units. We're trying to figure out all 3 angle measures and all 3 sides. So knowing that this angle is 37 degrees, if I call this alpha up here, I know that alpha, because 37 and alpha are complementary angles, they sum to 90 degrees. That will be 90 degrees minus 37 degrees, or 53 degrees. So there's our missing angle. We know the other angle is 90 degrees. And then if I want to figure out the other 2 sides, say I label this triangle A, B, C. Then this side will be little b and this side will be little a. If I want to find side B, I know that I have a 37-degree angle here, and B is opposite from that 37-degree angle, and I know something about the hypotenuse. So opposite and hypotenuse relates to sine. So I could say the sine of 37 degrees, think about that, is equal to b over 8. So the sine of 37 degrees is equal to b over 8. If I multiply both sides by 8 times the sine of 37 degrees, that will give me how long side B is. And if I do that on my calculator, making sure I'm in degree mode, you do this on your calculator while I write the answer out here, you should get approximately 4.815 units. So that's one of the missing sides. The other side, I could go through and solve for by Pythagorean theorem, but I'm going to stick with my trig since I'm practicing in this section. If I want to find side A, that's the adjacent side with the 37-degree angle. So I'm thinking cosine of 37 degrees is equal to the adjacent over the hypotenuse. So A will be equal to 8 times the cosine of 37 degrees. Again, on your calculator set in degree mode, if you do that out, we get about 6.389 units. So given this math that's on the screen here, we now know that angle A is 53 degrees. We know angle C was 90 degrees to begin with. We know that B is 4.815 units, and we know that A is 6.389 units. So that's the idea of solving for a triangle. You just have to match up what trig ratio, which trig function would suit the information that's given to you in the problem. Not too tough, just a little bit of thought at the beginning. One more problem, then I'm done, I promise. This last one says, from a point 340 feet away from the base of the Peachtree Center Plaza in Atlanta, Georgia, the angle of elevation to the top of the building is 65 degrees. Find out how tall that building is. So a quick review of angle of elevation. Angle of elevation is the angle going up from a horizontal. So if I draw the Peachtree Center, here's the Peachtree Center, and I'm at a point 340 feet away from the base of it. So I'm standing at a point 340 feet away from the base of the building. The angle of elevation to the top of the building, which is this angle in here, is 65 degrees. I want to know how tall that building is. So I'm trying to find H. That's the missing piece. I don't care about solving the entire triangle this time. I'm after just one thing, how tall that building is. So think about your 65-degree angle here. H is opposite, 340 feet is adjacent. So we need a trig function that deals with opposite and adjacent. And the trig function that comes to mind that I know I can do very easily on my calculator is the tangent function. So the tangent of that 65-degree angle of elevation is equal to the opposite side, H, over 340. In order to solve for H, we'll move the 340 to the other side by multiplication. So H turns out to be 340 times the tangent of 65 degrees. And we'll pull up our calculator. I'll do this one out for you. Whoops. 340 times, well, I don't even need those parentheses. Let me, you know, I'm thinking as I'm typing this that I'm not in degree mode. So I need to go over to degree mode. So 340 sine, no, it wasn't sine, it was tangent. Tangent 65 degrees. And we get that the building is about is approximately 729.132 feet tall. So here's an instance where we don't have to go through the extra work for solving for the entire triangle, finding all the sides and all the angles. It's just finding the height of the building that we were after. Make sure that you took thorough notes, rewind if you need to rewind at any point, and come in with any questions that you might have. Hopefully it was pretty straightforward. Not a super challenging section because you've seen a lot of it, I think, before from geometry class. All right, I'll see you in class.